So what I want to talk about today is one way that we use machine learning trying to construct collective variables for structural transformations. Interesting. Over here, and in particular in condensed phase systems, right? And so I'm coming from the rare event community. So all the things that I'm interested in, or most of the things that I'm interested in, are rare event problems, and they're essentially everywhere, right? So we've already talked about, or we've heard about rare events in terms of conformational changes that we have in molecules, larger biomolecules, protein folding, and so on. That's a big area of rare event problems that we have. Then also, of course, if we go into condensed phase systems, if we look into phase transitions, all of this is usually, we can consider this as rare events on a molecular time scale. In particular, if we want to look into things like nucleation and growth, and if we want to describe this on an atomistic level, this is very often a rare event problem. But also you have this, of course, in other fields, right? So if you have, if you look into weather prediction, right? So if you want to predict extreme weather or climate events such as heat waves or floods or anything like that, also these are rare events. And actually the problems that you have there, so the analysis of time series data and then the prediction of rare events is actually quite similar to what we have in molecular simulations. And then also, of course, something like earthquakes, right? We've experienced an earthquake, or some of us have experienced an earthquake this week. Others just didn't realize there was something. But again, if you want to predict earthquakes, you also have a similar problem in terms of a rare event that we have. And so, of course, if we look into molecular simulations, why do we have rare events, or when are we talking about rare events? And this is, of course, this problem of having a phase space where we have minima metastable states in our phase space, and these are separated by some sort of energy barrier over here. And so depending on what the energy barrier over here is, it takes a certain time for the system to transition between these metastable states. And that gives us a separation of time scale between the dynamics that we have within these stable states and the dynamics that we have for the transitions between the different metastable states that we have. And of course, what we can use then is some sort of like enhanced sampling schemes to actually be able to explore the entire phase space, and including all these transitions over here. And I have one slide that I've shown this many times now, but I really like it, so I also want to show it today. And this is about getting a feeling, or getting sort of like an idea of what that means in terms of sampling and the amount of data that we actually create and the amount of data that we are maybe interested in or not. So if we're doing molecular simulations, classical molecular simulations, classical molecular dynamics, we're solving Newton's equations of motion. We're doing this in discrete time. So we're having a time step over here, and no matter what we do, we somehow have to keep a time step that captures the fastest motion in our system. And if we're having a classical system, then in the classical systems, this is usually the vibrations. And if we're looking into, for example, metallic systems, and we're just looking into the vibrations of metallic systems, then what we have here is that we have, let's say, a typical vibrational period of about 140 femtoseconds. This means that no matter what I do, if I want to capture this correctly and if I want to capture all the vibrations in my system over here, I will have to stick with a time step that is on the order of femtoseconds in my system. And so now if I'm looking into like relations over here, if I see what a femtosecond is to a second, that's about the same as a second is to about 32 million years in a system. So if I want to simulate 1 second in a molecular system with a femtosecond time step, then this is equivalent to simulating the last 65 million years with a time step of 2 seconds. So since the KT impact event over here, which presumably extinct all the dinosaurs and so on, all the way to nowadays over here, if I take a snapshot every 2 seconds, that's the same resolution that I would have if I was doing a molecular dynamics simulation with a time step of a femtosecond than just simulating a single second. And so that gives you an idea about, not only is that, of course, computationally super, super expensive, but also the amount of data that I have and the amount of data that I would have to search for, let's say, trying to figure out what were actually the important things that happened in the last 65 million years. So if I have a snapshot every 2 seconds. And in particular, if we think about rare events, we are not interested in, if I'm just going to go back here for a second, I'm not so much interested in actually what's happening in here, right? So I have a lot of data over here, I have a lot of data over here, but what I'm actually interested in is in this transition. I don't have a lot of data in this transition over here, right? So we really would like to be able to sample just this transition. And as I said, so one of the things that we're interested in is nucleation. And of course, that we know that we can supercool liquids over here, and that's of course due to the nucleation barrier that we have. That is this competition between the energy difference between the liquid and the solid state that gives us an energy gain, and the energy penalty that we pay by creating an interface between a liquid and a solid state. Just go back to replay this. And so if we have this, we can of course supercool any liquid, and then if we perturb it a little bit, we give the system a little push over here. It goes over the nucleation barrier, and it of course immediately freezes over here. And so the question again comes in: can we understand what actually happens on an atomistic level over here, and can we modify, let's say, the product of the nucleation, right? So if I want to know now, can I produce, let's say, a particular structure? Can I create a particular polymorph by modifying this nucleation event over here, for example, through seeding or changing the environmental conditions? Can I now create a certain structure that I'm actually interested in, right? And so this is something that Kristen was saying at the end of her talk. So maybe we know now what structure we want to have a particular property, but now we also need to synthesize this, right? So we need to know, how does the system get there? How can I not only say, oh, I want this property, now to get this property, I know what structure I need, but now we also need to know, how do I get to that structure, right? And so that's why we were particularly interested in these, let's say, in these initial steps of these nucleation events. In particular, if we're thinking about, let's say, making systems from a melt or so on. So I'm not going to talk about nucleation today, and the technique that we're using for that is mainly transition path sampling. What I'm going to talk about today is solid-solid transformations. And so this is mainly related to phase-bounded migration. So you usually also have like a nucleation event, but then also you have growth in different directions over here. And again, if you want to know, let's say, how a solid-solid transformation proceeds, you need to know what is the mobility of your different interfaces over here. And so this example, this is actually an experimental result that we have here. So this is in a colloidal system. So people actually made an experiment and they induced a phase transformation. And they were looking at the initial nucleation event over here, and then they were looking at the mobility of different interfaces in different directions. And how does that depend, let's say, on the interface structure, right? And that, of course, depends on, let's say, the mismatch that you have in certain crystallographic directions. It depends on what kind of structure does your actual interface have, and so on and so on. And again, if we want to understand this from an atomistic point of view, we need to be able to simulate, let's say, the phase-bounded migration in a system. And again, that's something that's not trivial, because you have certain timescales that are involved and the way that your energy landscape looks like. And then, of course, we've already talked about this a little bit this week. There's this problem of how can we use machine learning together with enhanced sampling in terms of reaction coordinate if we have this chicken and egg problem over here, right? So if I have a lot of data everywhere, I can use a lot of fancy machine learning dimensionality reduction schemes, or even just linear dimensionality reduction, depending on how complicated your problem is, to achieve a low-dimensional representation of my system, right? So that I can use that then to get some insight, but I can also use it then to use this low-dimensional representation for enhanced sampling. Okay, that's fine, that works. But very often, if I have something like this problem over here, that I have a rare event, I don't have the data, right? So I don't have the data, so I cannot have a CV. I can guess a CV, but then maybe I'm pushing the system in the wrong direction, and so on and so on. And so this is what is meant by this chicken and egg problem. And a few things people have been trying over the recent years to incorporate machine learning to solve this problem. So one is iterative approaches. So there are a few people that have tried to do this in an iterative way, in such a sense that you just start without a bias potential. You just do some simulations. You take the data that you have, you do some sort of dimensionality reduction on that, your most favorite flavor of dimensionality reduction. you use that as your collective variable. You start creating a bias potential. You keep on sampling a little bit more. You have new data. You redo the dimensionality reduction. You get a different collective variable. You keep on creating a bias potential with this different collective variable, and so on and so on. And you're trying to do this in an iterative approach. That works sometimes. Sometimes it doesn't. It's very difficult to see if you're converging or not. And there are all kinds of problems involved with that. And there's no guarantee that that will converge. But it's definitely something that people have been trying and keep on trying, of course, to make this work better. Another thing that I've just learned about this week is the work of Johannes that also Rafa was talking about, trying to learn together the collective variable and the bias potential in a high-dimensional space, essentially on the fly by again using, of course, the properties of trajectories and also a little bit what Max was talking about yesterday, to include the properties, essentially more or less the action of your path, sort of like in your loss function, trying to figure out what is the best way to go from A to B over here. And then another way to do this is something that I will be talking about today, is to use an approach where you actually only use the information from the state. So you don't have any information about the transition, you don't have any information about the direction of the transition, but you have information in the two different states that you're interested in. And you can train a machine learning classification approach with the information that you have from the states, and then you can use the decision function from that classification as your collective variable. Right? And so, of course, the advantage of this here is that you do not need to sample the transition explicitly. You only need to sample the stable states, and that's something that's much, much easier. So very often, if we know what are the states, we can have a lot of information within those states, and then we can do the classification network, and from that we can then derive our collective variable. Okay, so that's going to be the, let's say, the core of my presentation today. And just to maybe make this a little bit more clear what that means. So one of the first people that tried that for molecules was from the group of Vijay Pandey over here in 2018. And they did this for the most favorite toy model of molecules, which is the alanine dipeptide. And they tried a few things, and it's really fairly simple in the sense that you just have this the molecule over here, and then of course you need to again somehow create your input features. So in this case, what they did is they just used the sine and cosine of the dihedral angles over here, and then they trained a simple neural network for the classification of the two different states, the alpha and the beta states, just with information from the stable states over here in the system, and then they used the output of the classification neural network together with well-tempered metadynamics. And then they could show that if they use this neural network-derived collective variable, and they use this in well-tempered metadynamics, they can drive the system between A and B. And so you can really use this classification, let's say the classification function, as your collective variable in the system. And then another study, again, on small molecules. Again, the alanine dipeptide here is our dummy system, is in this study here from 2020. The idea is the same. You use the classification approach, and then you use the decision function to drive your transformation. But they did it a little bit more, let's say, a little bit more sophisticated way of classifying the molecule. They said, okay, we don't want to put the sine and cosine in here. We want to use something a little bit more, let's say, agnostic in a sense, that we just use all the distances between the heavy atoms. But that, of course, already gives you a fairly high-dimensional space, and it's, of course, nonlinear to separate the different conformers here in the alanine dipeptide. So what they said is, okay, so we're using here a neural network to achieve a nonlinear combination of our input features over here, and then we are in the let's say, the output, essentially, of the neural network, the last hidden layer in that sense. We put that, and then we do a linear discriminant analysis, which is just a linear classification type of thing, and that's going to be our collective variable. So they just use the neural network here to combine the input features in a nonlinear way, and then have a linear way of doing the classification. And they did this for the ion dipeptide again, and then they used this as collective variable in on-the-fly probability enhanced sampling. And what I'm just showing you here is a projection of their collective variable. They call this deep LDA, and the isolines of an isoline projection of this collective variable on top of the free energy in the psi and phi plot for the ion dipeptide. And you can see it's actually quite nicely how the let's say the classification, the decision function of the classification approach kind of like reproduces the free energy landscape. So that actually seems to work quite nicely. And so the type of problem that I'm interested in is not small molecules, not even large molecules. I'm interested in condensed phase systems and looking into phase transformation in condensed phase systems. And our dummy system, of course, is, I mean, the dummy system is Lennard-Jones. If you want to do something a little bit more complicated, we maybe use a simple metallic system that we have used here, for example. But they're actually quite interesting. So this is the transformation that we're looking into is a transformation between a body-centered cubic phase and an A15 phase, which is a so-called topologically close-packed phase. And when you find those in complex alloys, they form and they either beneficial or they are destructive in your materials properties. But you can also find them sometimes in like unary metallic, just elemental metallic systems. For example, here in tungsten, you find both. You find the BCC and the A15, and that's quite interesting because the BCC phase is something that you would like to have in microelectronics because it has a very low resistance over here. But then the A15 phase is something that you would like to have in spintronic devices because it has a very large spin Hall coefficient in the system. And so if you want to try to, let's say, selectively either grow one of these polymorphs in your tungsten over here, you can do that. You can tweak the system around, but then maybe it also might transform again back and forth, depending. For example, you can do this in like thin films and stuff like that, but it's not clear why it transforms from one to the other, and the transformation itself is also not fairly obvious because they don't really fit together, and so it's not clear. And so this was our dummy system. Now that we said, okay, let's try to do this in a condensed phase system, try to drive the structural transformation between these two condensed phase systems using the idea of classification in the system. And of course, if you're in a condensed phase system, you can't really do like a global description of your system, but you somehow go to a local description. Right? So we're trying to use our machine learning approach here to characterize local environment, to classify different local environments, use that then to define some sort of like a global classifier that gives us a difference between, for example, these two states over here, and then describe this transformation here as a path in this classifier space. And of course, what we're thinking about then, of course, is that, okay, well, if we're transforming from here to there, somehow we have to drive structural transformation at this interface, right? So we have to figure out how does the system transform. But on the other hand, as always, we don't want to be we don't want to tell the system how to do it, right? So we want to give it as much freedom as possible, while also kind of like figuring out what is a good way to actually bias it to do what we want it to do. And so the network that we use is, of course, that's not something fancy. It's a very simple MLP over here. You just have, so the input is for every atom, you just put in the atom and some environment. You compute a set of features, and that I'm going to talk about that a little bit more because that might be some of interest, a little bit more interesting. That's very simple. And then your output is just a simple classification. So you just have n classes over here that then tell you essentially, if I'm looking at the local environment of this particular atom, which of these environments or which of these crystalline structures is this most likely to be, or is this most similar to in a system? So that's the whole idea of doing this in a local way. And of course, if you think about this is the very same idea of what people do when they fit machine learning potentials for these things, right? So they also use the local environment, but then of course the output is this is just regression, and the output is just one energy value. whereas in this case it's classification, and you just pick one of those in your system. And so if you want to choose your input functions, we have this obvious requirements like the invariances that we've already heard quite a bit about. In our case, they also have to be differentiable, because remember, in the end, we want to use this in enhanced sampling. That means we want to compute a force on our atom. And so whatever collective variable we derive, it has to be differentiable with respect to the atomic position. Hopefully, we'll find something that has a simple functional form, again, just for performance, essentially. Short range is the same idea. It should be short range just because it's going to be cheaper if it's short range. And if the number is small, that's also useful. And I'm emphasizing this here again because already whatever we're doing in the enhanced sampling is very expensive, right? So we need loads and loads and loads and loads of computational steps. So having something that's efficient is actually quite important to do that. We're using a cutoff function that's also obvious. And again, this just needs to be smooth because it needs to be differentiable in the system. So the most obvious choice, if we have something local, is to just go for the Bela-Parinello symmetry functions. And that's also an idea that was initially was done by Christoph Delago and one of his students. And they did this to distinguish different phases in ice. And so you have the radial symmetry functions that just depend on the distance between two atoms. This one is just the coordination number. This one here is essentially just, you can think about it like putting peaks on your RDF, essentially, more or less. And this then is a cosine function of your distances, so you can kind of like enhance or extinguish certain peaks in your radial distribution function. And then, of course, you can include angular symmetry functions so that you have like your three-body interactions in this. And these work fairly nicely if you want to compute energies. And also, Christoph, they showed it works very nicely if you want to distinguish ice. But they used, like, I don't know what they use typically for neural network potentials, probably for each atom 80 or more. In the ice classification, they used, I think, 60 symmetry functions for each atom to classify this. And that's a lot, right? So we don't want to do that and then compute this and then in every step get the force, and it's like a lot. So we said, well, it's a little bit simpler than computing an energy, and we already know a lot about the system in terms of structure and so on. And then, of course, the obvious way to include is the Steiner bond order parameters, because they are, of course, used very often in doing the structural characterization. But just using those is not sufficient for something like this weird A15 phase. But that doesn't matter. We can still just compute the Steiner bond order parameters. They're again based on the spherical harmonics, and we can use them as one of our input functions with different values of L in the system. And they, of course, then contain already all this angular information. And what we then found for our system here is that we can get away with a very, very small number of input functions. So we can take 3 of the Steiner parameters with the L, 6, 7, and 8 for our system with a fairly small cutoff radius over here. So that's essentially just like kind of like the first coordination shell in our two different systems over here. And then we need only 11 of these radial symmetry functions. So we don't even need any of the angular ones because all the angular information is already in here. So we can use a very small number of those with a slightly larger cutoff, but all of this is still fairly cheap in comparison. And then as an output, we use, of course, the things that we have, the BCC and the A15, but also we include a few other ones like FCC, HCP, and so on. And we include a disordered phase, which we train in the liquid and which we also train with configurations that we find at our interface over here, because we also need to be able to figure out what are the interface configurations over here. And so just one word about the loss function that you can use. So it's, as you know, I mean, the efficiency of whatever you do very much depends on what you define or how well you define your loss function over here. And of course, for classification, the most obvious one is just the loss function over here, where you essentially say, okay, this just gives me the probability that my environment belongs to one of the classes, and then your activation function in the output layer is just a softmax function over here, which just ensures that everything sums up to 0, and that just gives you a probability. We use the loss function that's slightly different, but it's very much related, which just means that your output belongs to any of the classes. So in principle, they could sum up to something that's larger than 1. We also normalized it and so on, and it really didn't make much of a difference. So in a sense, this is just like a sum of like the cross entropy for each of the classes over here, and then your final output layer activation function is just a sigmoid function in the system. And if you look into the classification problem, it's much easier than predicting an accurate energy, right? So if you predict an accurate energy, that's very, very difficult. For classification, it's much, much, much simpler. So here we have 25,000 test data. So the way that we create the test data is, of course, we just run MD, and then we just pick out the atoms, as just in the normal, or other kind of like training things. And one thing that we do here is that we say, either if all of the outputs have a value that's smaller than 0.5, or more than 1 has a value of 0.5, then it's undefined. So that means actually the network doesn't really know what kind of structure that is. It just gives us a low probability for everybody, or it gives us a high probability for 2 of them, right? So that doesn't make any sense. And what you can see here is, so this is 100 training data, like literally just 100 training points, and a network with 2 hidden layers with 5 nodes each, and you already get like a fairly good classification result. And this is, of course, we can massively just throw a lot of data on this and increase a little bit. This is still a small and tiny network over here, but even if we increase this a little bit, our accuracy is very, very high, right? So it's not a difficult learning problem in that sense. So the challenge comes in, and this is just to visualize this. And so here now, this is always the same snapshot, and it's just colored according to the output of the network for the different classes that we have. So this is colored according to the BCC output, this to the disordered, this to the A15, and FCC, HCP, we don't have anything in here. But now we, of course, need to have like a global description. And so what we're doing here is that the simplest way to do this is to just take an average. And so that just gives us a phase fraction. No? And then you can say, okay, that's great. So now essentially we only have 5 in our approach. We only have 5, let's say, different phases. So we had 5 classifiers. Now we can do enhanced sampling in that. And we actually tried this. So we even tried it to just do it with like BCC, or just tried to do it with like the capital Y, BCC and A15. But it's not working very well. And the reason for that is, of course, that these are all related, right? So they're not independent. You cannot just increase the amount of BCC without changing somebody else, right? And so it doesn't work. If you just take them independently and try to bias along these different order parameters, it's not really working well. And so what we did then is that we said, okay, well, let's combine those. First, we combined them in a linear way. Of course, that also didn't really work. And then we said, okay, let's try to figure this out in terms of combining our global classifiers in some sort of nonlinear way.
Quick question.
Yeah.
So the global classifier, do you backpropagate on the actual loss on the global classification?
No.
So why not actually? Because that would make that classifier a lot better and might start correlating.
Because we don't have a global input. We only have a local input.
But you do have global output though. Or?
No, it's a local output. So you.
But you never have a global.
I never have a global output. I always just have a local output. There's no global quantity that I'm training. So I'm just having an output for every atom, essentially. But in my enhanced sampling, I need something global.
How do you know? Yeah. So I'm just a bit confused about the fact that you try to apply it to something, and you probably need to test whether you're doing well or not on that something. So you have some ground truth labels for your test set, I guess, to figure out how well your classifier is working.
Yeah.
And so why do you, if you have some labels for your test set that are global.
They're not.
But how do you then test the performance of the global classifier? You can never test that?
No, you don't. So it's just like, so the only thing that we're classifying is, so every atom, so our classification problem is essentially on the local environment of my atom.
So you have no idea how well it does for the global classification problem?
No. No, but you, in a sense of saying that, okay, so I have a structure and then you say, okay, this is 50% of this and 50% of that. No, we don't. So it's just a sum, it's essentially just a sum over the local environments, essentially. So if we look at this here, if we look at these pictures over here, so these values are just the average of the output of everybody.
I guess I'm confused about the fact that you're trying to create something, so some sort of bias potential from one state to another state.
Yeah.
But you never have actual examples of these states, of the full state, A and B, the global
Exactly.
state.
Exactly. But the idea, of course, is in this case, the idea is that you're driving the transformation through changes in the local environments. That's the underlying idea then. Yes. Yeah. And so the way that we combine them is we put them in what is called a path collective variable, where you have this expression over here, which is your path function. And if you look at this sketch over here, you can see if you're defining a path, so this is now in 2 dimensions, but you can do it in arbitrary dimensions if you want, then your path function is a continuous function that goes from 0 to 1 along the path, and it's locally perpendicular, it's constant perpendicular locally to the path. And the other function that you can then define is also a distance function over here, which is kind of like an envelope around that. And so you can use this path collective variable to drive your transition from one point to another, and you can use this, for example, in sort of like a restraining potential, right? So if you want your system to stay close to your path, because perpendicular, it could just move without changing the value of your path function. But if you want to constrain it, you could use an additional restraining potential on the Z function over here. And so if we do this now for our path fraction, so to speak, that's of course fairly easy in a sense that we say, okay, well, using BCC and A15, so now we want to go from here to there. What does that mean in our classifier space? That means that I'm going from a point where I have very little BCC, 0.2, and a lot of A15, 0.5, to something where I have a lot of BCC, 0.65, and a little bit of A15, which is only 5% in here. And if we're just assuming that it's something like this, then we just say, okay, this is a linear path in this classifier space. So our path collective variable now is based on this particular path, the red path over here, and the path function is the color function that we have. So we can drive the system from over here to over here by driving along this path collective variable from 0 to 1, which means that we're driving the system from such a state to such a state in the system. And so what we're using here is the first thing that we tried was the DFAT that Mark already introduced in quite some detail in his presentation. So we have an extended Hamiltonian approach, and we couple this to an extended variable, and then we have our collective variable. In our case, this is the path CV. Over here, this is the extended variable in the system, and then we just have to make sure that the mass that we're choosing for our extended variable is much, much larger than the effective mass of our path CV, and then we can run the extended variable at a much higher temperature, and then we can recover the actual free energy in our system. So we can recover a free energy profile along our path collective variable in our system. And that's what we did. So we only have one. So now, since the path CV is one-dimensional, that becomes a little bit easier here. It's just one variable that we have to drive along in the system. And so what you can see here is that the actual system is at 300 Kelvin. The extended variable is at 3,000 Kelvin. So it's really a much, much higher temperature. The mass ratio is about 1,000. And this is, for example, in this case, this is our coupling constant that we have over here. And now, so here now you can see the change in our path CV as a function of time. And so this is a couple of nanoseconds that we simulated to drive the system from this configuration to this configuration. And if you were running this at 300 Kelvin, which you actually can't in the system, that would be like, I don't know, milliseconds or something.
Somebody's walking on the roof.
Hope it's not falling on me. So you can really do like a really, really fast exploration. What you can also see is that you have these plateau regions over here, which comes from the fact that this performs sort of like a layer by layer transformation in the system. And so if we look at the free energy profile for this, we can also see this layer by layer transformation in the system. So here what I'm plotting is the potential of mean force for these simulations. So we have extracted the potential of mean force by doing many of these calculations. And what we get is something like this, like an energy profile that looks like this, where we have always a transition, like we're forming one layer by the next, and we're getting like a barrier that's about half an electron volt. So the meaning of this barrier might not be particularly meaningful, because this is like a super small system, and of course if it's larger you don't have like a layer by layer, but you have like a nucleation and growth mechanism and so on and so on. But it's consistent with like effective barriers that we got from adaptive kinetic Monte Carlo and very high temperature MD simulations for this particular system. And so we can actually recover, let's say, an effective barrier for this layer transformation, which is connected to the interface mobility in this region. If you make the system larger, so we tried this for larger systems and different orientations and so on, and then you can really see different interface mobilities. And what you can also see is that for some directions, you actually have a difference between, let's say, a high temperature MD mechanism and a low temperature driven mechanism, because at the high temperature, you're just like pushing the system over, but at a lower temperature, for example, it then just finds the direction or the orientation that has the fastest interface migration, so the highest mobility of the interface in the system. But of course, this is only one-way transition, and this is why this is fairly symmetric, but actually we would like to drive it in both directions, and we couldn't really do it with DFT in the system, and the reason for that is that it's a very asymmetric energy profile, because BCC is much more stable in the system. So we did this also with metadynamics in the system, and what you can see here is that initially, fairly quickly, you're driving the system from 0 to 1, so you're making one transition over here, so you're creating all the BCC. But then you really have to come back, and you can already see here, so this is 120 electron volts, so this is huge, right? You slowly have to build up your bias potential as you go along, but then eventually we're filling in this whole bias potential, and this is what you usually want in metadynamics, so that you get this diffuse behavior going all the way up and going all the way down in a given time frame. And you can see here now how asymmetric this landscape is, but you still have these bumps, right? So you still have this layer transformation behavior that we already saw in the just in looking at the forward transition, which is essentially this first line over here. And so this is what that looks like in the movie. And the interesting part here maybe is that you have, if you look at this transformation, you always have this very disordered interface region, and the kind of like it rearranges. So it dissolves and then it grows, the actual crystal structure grows into that. So we really have like a transition through a disordered interface region. And the nice thing about these collective variables that we have is that they don't care about that, right? So they don't tell the system how to transform. They just tell it, well, try to transform an environment that looks like BCC into an environment that looks like A15. But how you do it, it doesn't really tell the system anything about it. And so this is actually quite nice in the sense of trying to have a collective variable that is not impacting the mechanism, or at least it's not impacting it too much, let's say like this, right? And so one of the things, okay, why does that work? Because this is now a very complicated thing, and it goes maybe a little bit back to the question that you had earlier. Why would that actually give us something sensible? So if we think about the DFT, so what we have here is the coupling potential, right? So we have this is our path collective variable, and this is our extended variable. And so these are coupled by this harmonic potential that we have. So if we want to look at the biasing force that we get on every atom, which is in this sense the coupling force, so it's just a partial derivative of our coupling potential with respect to our path collective variable, and then the derivative of the path collective variable with respect to our atomic positions. Now, if you think about what I've been telling you over this presentation here, is that we have the positions They go into the symmetry function, they go into the neural network, that gives us the classification output, that goes into the global classifier, and that goes into the path TV, right? So it's a very long chain rule of derivatives. So why would that give us forces that are sensible in any sense and actually do what we want them to do? So if you look at the forces, if you look at the magnitude of the forces, then what you can see is that actually the biasing forces, they're usually large, for example, in our case, close to the interface, and they're fairly small whenever you are in a perfect bulk environment. And if you now compare all the different terms in your derivatives over here, what you can see is that the difference, if you have a large or a small biasing force, the difference actually comes from let's say, the partial derivative of the output of your classification neural network with respect to your input functions. So whenever you are very well within your classification part, so if you're not close to, let's say, the decision boundary of your classification function, these derivatives are small. They're very small. They're very close to zero. And they're only going to be large whenever you're getting close to the decision boundary. And that's actually nice because that's exactly what we want, right? So we want to push systems away from like a weirdo environment into like one of those environments. Yeah.
Wouldn't that mean, though, if you would start with either fully BCC or fully A15, that nothing would happen?
Yeah. So we haven't tried this for nucleation to apply this. So in this case, we always have an interface. If you want to get, let's say, if you would like to get a transition where you have also the nucleation event, the initial nucleation event, that probably doesn't work because you don't have anything different, right? So you don't have anywhere to go. You would have to somehow promote these initial fluctuations. Yeah. Okay, so just the last few minutes is just so I've shown you this for this A15 BCC system, and now of course we also want to do this for molecular crystals. It's the same story. It's just like it comes with all the problems that we have, and why are we so interested in that? And so one thing is that so Alex already talked a little bit about different polymorphs and what kind of impact they can have, and we have some colleagues at NYU that did some really interesting experiments for contact insecticides. So contact insecticides is the stuff that you spray on walls and that you spray on nets to do malaria prevention. And so this is quite important. But of course, whenever you put something into the environment that kills a certain part of animals, it's not really great either, right? So people try to use as little as possible and make it as efficient as possible. Now, what they found is that if they take a certain contact insecticide, like this deltamethrin over here, and they just crystallize it in different polymorphs, so different crystal structures, exactly the same thing, and they put this into a petri dish, and they put like mosquitoes and these other insects in there, it actually matters what's the crystalline form of this insecticide, which is a bit weird, and nobody actually knows 100% why that is, but usually it's the metastable form that it exhibits a much higher efficacy. So somehow that must be related to, I don't know, how the molecule is absorbed, because it's not the let's say whatever it does to the animal, because the molecule is the same, right? So the neurotoxin is the same. But it has to do with somehow they're walking over this, and then maybe they're ripping off patches, and maybe that's easier in a metastable form. Nobody knows. And the effect is quite huge. So this here is the knockdown percentage as a function of time, and you can see this is like a factor of 10, right?
The molecule is in a different isomeric form?
No, it's slightly different, so it can have like a slightly different conformer, but not so that you would say that this conformer is more poisonous than the other. And I don't. So from a let's say from a barrier point of view, once this is absorbed, I don't think once this is like in the liquid environment that would matter. Yeah, it must be somehow the crystal. So of course the idea is, can we now produce reliably this more metastable form, and more importantly, can we stabilize it, right? Because usually the more metastable form is less stable, so it converts into the more stable form. But so if you're spraying your walls with this contact insecticides, but after whatever 10 minutes it transforms into the other one, you haven't gained anything. So can we somehow kinetically arrest this more metastable form in terms of like, can think about it like an inverse catalyst, right? So you don't want to change the states, you want to just increase the barrier for the transformation over here. And can we somehow figure this out from let's say, from a computational point of view? First of all, how does this transformation work? And then can we somehow modify it? Can we kinetically stabilize these metastable forms and make this more efficient? That's what we're aiming for. What we're starting with is something more simple, of course, as always. So we started with urea crystals because urea is simple, it's flat, it's rigid, it doesn't do much. But it has a lot of polymorphs. And so we wanted to see, can we do the same sort of classification-based collective variable and drive the transformation between two polymorphs in urea over here. And so it's again the same idea. You have a molecule, you try to identify the environment, classify the environment. Is this like which polymorph does that correspond to? But as everything in molecular crystals is more complicated, you have to somehow get like a feature engineering that kind of like can represent this. And also, if you think about what I said before, right? So you're driving the transformation by somehow like getting a biasing force that is connected to how your coordinates feed into your input features over here. So what would be a suitable representation so that actually, to make this actually work for these molecular crystals? And one way to do this, of course, you can use a point vector representation and then maybe combine this with the symmetry functions. And this is what we started out with. So point vector representation just means that you take, for example, one of your atoms in your molecule, and that's kind of like giving the position of the molecule. So if you're exerting a force, you would move it around. And then a vector representation gives you the orientation of the molecule. For example, in this case, it's here between the carbon and the oxygen and between the two nitrogens. And you can, of course, now imagine if you put this into a symmetry function, you're exerting a force that would kind of like rotate your molecule in the system. And this is what we started with. And so you can then use the point distances. Now the capital I here is now per molecule, essentially. And the Rij is now it's a distance between the point representation between two molecules over here. You can put this again into these radial symmetry functions over here. And then we did the same with the angle between vectors. So if I have two molecules and I can compute the vector on this molecule, and then I have another molecule and I can compute the vector on that molecule, it will tell me the relative orientation between the two molecules. And then I can again put this into some sort of the same form of symmetry functions to determine what's the relative position of the molecules with respect to each other. And if I just do classification again, classification is not, let's say for something that's not too similar, it's not such a hard problem, and you can do it quite well in a sense that here now we again created an interface between a urea 1 and a urea 4 crystal, and then again the coloring here is according to the output of our classification or network, and you can see that works perfectly. There's not a big problem. But now again, can we use this to construct a path corrected variable and then use this in a sampling? And this is something that is still very much work in progress, but we've managed to actually get it to move a little bit over here. So now this is essentially the same setup that I showed you before, except now we are using UFET. And if you remember from Mark's talk, what he was saying, in UFET you do metadynamics on your extended variable, essentially, right? Because if you do metadynamics, it might sometimes a little bit hard on the system, but if you do metadynamics on the extended variable, that kind of like sometimes it's a little bit smoother, it works a little bit nicer over here. And what you can see is that we can actually do that, right? So it's not perfect yet, but we can sort of like drive a transformation between these two polymorphs. And again, if you look into the plots over here, so this is the evolution of the path collective variable. This is the evolution of the path fractions that we have of the two polymorphs over here. And again, this is a time scale of nanoseconds where we can a little bit move this interface back and forth. Not quantitatively yet, but qualitatively, we got it to work for the system at last. And then, of course, the goal is to do this for this more complicated ones where you also have conformational changes and so on and so on. No? Okay, so that brings me to my summary of our presentation today. So what I wanted to show you is how we can kind of like derive, maybe in a little convoluted, a little bit more complicated way, reaction coordinates from machine learning classification So we're mixing this, right? So it's not just machine learning, but we put a lot of physics in it. And then machine learning helps us to utilize the knowledge that we have and put it into something that is still not too specific, right? So that impacts the system maybe not too much. So we're using the decision function of the classification to drive the system between two states. And two states now, what I mean is local environments. Because if we're looking at structural transformations in these condensed phase systems, they're essentially induced by changes in these local structural motifs. And so if we're doing that in the enhanced sampling, then we can essentially promote these local rearrangements in the system. And then do this, and as I said, so what we want to do is we want to do this for this weirdo, slightly weird insecticide molecules, and hopefully figure out why one polymorph is, or how we transform one polymorph into the next. And with that, I just put up my acknowledgement, and thank you for listening.